Okay, we consider a situation where a ball rolls off the end of a ramp, falls to the floor. And we know the speed, not the velocity, I don't have an arrow over this, just the speed with which the ball goes off the ramp. We don't know the angle of the ramp, we don't know anything else, we just know how fast it goes off the ramp and how far it falls. Now how far it falls was given as delta y, not a vector delta y, just we know it falls a distance delta y. Now there's a vector delta y that goes along with that, and that's a vertically downward vector of magnitude delta y. Okay? Okay, well, we want to solve this problem. We can't analyze the motion of this thing because we don't know the angle of V0. We don't know the angle of the ramp. We don't know what mix of horizontal and vertical velocity we start with. But we do know how far we fall, and we know how far we go in the x direction. Now actually from that information we could analyze the motion, but that's not what we're doing here. We want to analyze the energy. Now, first of all, the work done by the net force is the vector F net times the vector delta S. Okay, the vector delta S is our displacement, the F net is our net force, and this is for the case when we have a constant net force. We just multiply that constant, we can take the dot product of that constant net force with the net displacement. Doesn't matter how we get from the first point to the second, we multiply by the displacement vector, and we get the work, and that's equal to the change in kinetic energy, which is the change in 1/2 mv squared. Okay. Now we're going to use an x and a y axis that are horizontal and vertical. Okay, and we're going to model this. Okay, so in this case, our net force is said to be just the gravitational force. So that's mg in the downward direction. Well, the j vector is in the positive y direction, so that the F net vector, which is just again the weight, is negative mg times j. Our delta y is just our scalar delta, our delta y vector, and we could actually call this our delta s vector. And that might be a little bit more consistent with the notation used here, so I'm actually going to change that. I'm going to call that delta S, and I'm going to call it delta S here. Okay, our displacement vector, and I called that delta S, and I shouldn't have called that delta S because I used delta S over here for the vector. And our displacement does have an x component, so that was rather ignorant of me. Okay, so I'm still going to call this delta y. And that's going to be, well, delta y, scalar delta y is how far we fall. And if we fall, we're going in the negative j direction, so we have delta y of negative delta yj. Now, our delta s, from here to here, and I haven't drawn that vector because people still want to draw a straight line from here to here to indicate the path of the object, totally ignoring the fact that it speeds up as it goes down but not as it moves across. It speeds up in this direction, not in this direction. It speeds up throughout the whole thing, but ignoring the reasons and the fact, the reasons for and the fact that the shape is parabolic. Okay. So I didn't want to draw a delta S, but it would go from here to here. Doesn't mean that's your path. That means it's a vector from where you start to where you stop. Since the net force is constant throughout, because the net force is just the gravitational force, we can just express the work as F net dot delta S. We don't have to do an integral or anything. So we have a delta S vector, which is just our delta x, whatever our displacement in the positive direction is, minus delta yj, which is our displacement in the y direction. Now remember that, well, I don't want to make that distinction. Delta x is regarded as our displacement in the x direction. Delta y was given as a distance, so that negative delta y in the j direction is actually our displacement. If that doesn't bother anybody, don't worry about it, but if the difference between a displacement and a distance is worrying you, there's your explanation. Okay, well, then F net dot delta S, which is our work, is going to be equal to F net, which is our negative mgj, dotted with our delta S, which is delta xi minus delta yj. And that's going to equal what? Negative mg times negative delta y, mg delta y. Our j component multiplied by our j component. There is no x component here, so we actually have 0i, which multiplied by, so the 0 on the I here multiplied by the delta x on the I here gives us 0. So clearly this vector dotted with this vector gives you this, and that is the work. Okay, now remember, delta y is not a negative quantity. Delta y was the distance we fell, not a displacement, so that this is a positive quantity. So 1/2 mvf squared minus 1/2 mv naught squared, well, that is the change in 1/2 mv squared from the initial to the final point, is just equal to the work done by the net force, which is mg delta y. And we then solve for vf, obtaining a very straightforward result. Note that this result is independent of two things. It's independent of the direction of the initial velocity, and it's independent of the mass of the ball. So, here's our result for VF. We never had to analyze an equation of motion or equations of motion in 2 dimensions. The 2 dimensions were taken account of by the fact that we did this dot product. We had a 2-dimensional vector here, which actually only had one component, and a 2-dimensional vector here, which had an unknown xi component, let's say. We don't know how far it went in this direction, and it doesn't matter. Okay? We still get this result, giving us this result.